Okay, so now I want to go through a couple of other situations that can be modeled with first order differential equations or from the continuity equation. So let me just go over. This is section 4.2. Sometimes the thing that we're modeling can actually be velocity of the thing that we're studying. So let u be the velocity of some one-dimensional substance. Okay, so this could be water in a pipe, it could be, gas flowing in a pipe, it could be people, walking in a line, it could be cars walking, going down a road, whatever. The velocity of something that's just moving in one dimension. And always we're going to assume, if we have water flowing in a pipe, there's not water flowing into the pipe other than just, here and here or something, right? And there's not like a hole in the pipe where water can flow out. If it's a road, there's like a turnpike situation where you get on the road and stay on the road and so on and so forth. This is just to, obviously in real life we might have to consider some of those things, but this is just to make the equations, it's like a first pass and an approximation based on the sort of things that get modeled. When we get to cars, you'll see why, this is, when we're dealing with traffic is obviously one situation where there's cars coming on and off all the time. But I think why this assumption makes sense will begin to be clear for what we're actually trying to model with traffic. That'll be a couple videos from now. Okay, so let u be the velocity of some one-dimensional substance. If I look, let's say it's flowing along a pipe or a road or whatever. Now, if I look from A to B, I can define a quantity that is going to be the momentum of whatever is moving between A and B. So remember, momentum is mass times velocity. So if we have something like rho of xt is linear mass density, okay, now if it's water flowing, it's pretty clear what linear mass density is. It's the kilograms per meter or whatever. But maybe you define some other similar quantities and some other similar notions of momentum if you're modeling something else. But the momentum is going to be the integral from A to B of mass times velocity. So velocity is going to be u of xt, and then the mass is going to be rho of xt times dx. If rho of xt has units of kilograms per meter and dx has units of meters, this has units of meter. This is velocity times meter. So this is a differential form of this, like the differential momentum, and we're adding the momentum up from all of the points from A to B. So this is the momentum in the integral A to B. Okay, now how can momentum change? Well, it's going to be equal to the momentum flowing in at this point minus the momentum flowing out at that point. And of course, I'm already thinking about doing something like this. The t derivative of q is equal to the integral from A to B of the t derivative of u times rho. And I'm already, dropping the arguments. That is the x and t's. I'm not going to write those right now, just because it gets a little too cumbersome. Okay. Now, what are the only two ways where momentum can enter? Well, it's going to be through A and B. Now, the amount of momentum entering is going to be equal to the velocity times the flux. Okay, so the amount of momentum entering at point A is going to be equal to rho of AT times u of AT. This is like the momentum density times u of AT. That's the velocity. If we think about what the units are here, let's just think through the units here to do a little sanity check to make sure this makes sense. So rho here, let's say the units are something like kilograms per meter. Okay, U of AT here is going to be units of meters per second, and then U of AT here is going to be units of meters per second. And what we get here when we do all of the cancellation of the units, we're going to get, okay, so these meters are going to cancel. We're going to get kilograms times meters per second. So this right here is momentum, and this is per second. So the units of Q prime is momentum per second, and this is momentum per second. So again, what we have is sort of a momentum density type of thing times how much it's flowing, which is the velocity. Okay, so now if we just consider the only sources of momentum in this is going to be like the momentum flowing in from particles flowing in. So there's a flow happening here, right, of particles. So if we only consider that the change in momentum in this area here is going to be to new particles coming in or particles leaving, or again, it could be particles leaving this way or particles coming in that way, in which case we're going to have different signs. But conceptually, we think about particles flowing, flow being to the right with a negative value being left flow. Anyways, conceptually, we have particles flowing in here and out there. If we only, this is a big if we only consider that the increase of momentum in this interval right here is due to new particles coming in or current particles leaving, then the difference in momentum is going to be equal to this minus the thing at B. So minus rho of BT, and I'm running out of room. Notice this is just U of AT squared, so it's going to be U squared of BT as well. Well, we can write this as minus the integral from A to B of the x derivative of rho times U squared dx. Well, these two things are equal to each other, right? They're just different ways of expressing the same thing. And so what this tells us then is the t derivative of rho u is equal to minus that, or just I can add it over and we get it's equal to the x derivative of rho times u squared. Sorry, you add them together and you get 0. Okay. Now notice that if rho is constant, so let me just say this. If rho is constant, I'm not going to rewrite this. If rho is constant, we can simply divide it out by rho. Okay, because we can pull it out here, divide over to 0. And now what we have is the x derivative of u squared. So by the chain rule, this gives us 2u times the x derivative of u. Now this is a famous equation called Berger's equation. I don't know enough about the history. I meant to look this up, but I didn't. I don't know enough about the history of this equation. Okay, so this is modeling a fluid, the velocity of a fluid that has some strange assumptions. For example, as we will see in just a moment, it's going to model a fluid where there is no pressure difference, but also it is compressible, because typically for an incompressible fluid, well, anyways, typically for an incompressible fluid, the x derivative of the velocity is going to be equal to 0. That's not what we have here. Otherwise, this just becomes the t derivative of u is equal to 0. Okay, so again, I don't know if this actually models any real-life fluids to any great extent, but it's a very important equation because it's going to be it's a very simple equation is going to model shock formation, and we'll talk about that in upcoming videos. At any rate, this is what we have here. Okay, but in reality, as I say in my notes, this model is a simplified model and it leaves out pressure. That is, it says the only way momentum can flow into an interval is by the substance itself moving into or out of the fluid and either adding to or subtracting from the total momentum. Okay, but we know that's not how momentum works. If I have these swingy ball things, right? If I pull up a ball here and let go of it, the ball swings down and the ball over here on the end swings up. Well, the momentum over here has increased, but it's not because the moving ball here is now in this area. The momentum is 0 over here, and now it's positive over here, right? So momentum can travel through objects. And in this case here, the momentum that's traveling through the object is pressure. That's exactly what pressure is. But it's possible for momentum to travel through objects, and then I even mentioned the silver bell example, or the silver swinging balls example. In this context, that's pressure. If we think about pressure as pushing to the right, so if you think about pressure as pushing to the right, so like right here and right here, another way that we could have an increase of momentum is going to be the pressure on the left-hand side minus the pressure on the right-hand side. Okay, and now pressure is typically taken to be a function of the density. So we could have, in addition to this, right here, we could have something like, this right here is the contribution of momentum to the actual particles entering and leaving this region, but we could also have the pressure evaluated. So now here's, unfortunately, I'm going to be using P and rho. These are just the common notations. I'm going to try to make it clear what's a P and what's a rho. So this is a P, and then this is a rho of a T minus, this is a P, and that's a rho, like this. Okay, and then we can just combine this into one integral, again using the fundamental theorem of calculus, and this is going to be minus the integral from a to b of the x derivative of rho u squared plus p dx, like that. Okay, and so now what the equation would become then, I'm going to write it over here, so I'm going to get rid of this because I don't think I'm going to need it for right now. What we're going to get on the left-hand side is going to be the t derivative of u rho is equal to, or sorry, let me say plus the x derivative of rho u, and it should, I made a little mistake over there, it should rho u plus p of rho equals 0. So this p, this is p of rho. It almost seems ridiculously absurd that I should be using P and rho, given that they both look alike in general, but definitely when I write them. So that's a rho here, and this is a P here. But some things I don't realize, that looks even more like a rho. I'm moving away from the ideal now. I can't do a P now. That's what's happening. Now I can't write a P. That's a rho, that's a rho, that's a P, that's a rho there. Okay. Now, in addition to this, the quantity rho is also conserved, and we've seen different conservation laws that would apply to this. And this says that the t derivative of rho plus the x derivative of u rho is equal to 0. And now we have a system of two equations. So rho and u are unknown. The pressure function, we typically know what the pressure function is. A lot of times it's modeled as like an exponential. So p of rho equals rho squared, something like that. Okay, and it just says, if p of rho is equal to rho squared, what's happening here is the greater the density, the bigger the pressure. That's what this would say here. Okay, so again, this gives us a system of two equations now. We have two unknowns. This gives us a system of two equations here. Okay, that's all I'm going to mention on these equations. This is kind of like fluid flow equations. And then I'm going to look, in the next video, I'm going to look at a traffic flow model that will give us a way to model traffic flow.